Hello and welcome. Tonight, we are going to drift through 100 relaxing facts about the universe. There is no need to remember them all, no need to focus too hard. Just let each fact pass slowly, like a star moving across a quiet night sky. Some of these facts are about planets, some are about stars, some are about galaxies, black holes, cosmic time, ancient light, and the strange hidden structure of space. Together, they form a gentle journey through the universe, from our small planet to the edge of what we can observe. So settle in, let the room become still, let your breathing slow, and let the universe open quietly above you. The universe is about 13.8 billion years old. That does not mean we can see every part of it, but it means the hot, dense, early universe began expanding and cooling almost 14 billion years ago. The light from the sun takes a little over 8 minutes to reach Earth. When you feel sunlight on your face, you are feeling energy that left the sun several minutes earlier. The moon is much closer than the sun, but even moonlight takes a little over 1 second to reach Earth. The moon is close by cosmic standards, but still far enough that light needs time to cross the distance. Earth is moving through space all the time. It rotates once each day, orbits the sun once each year, follows the sun around the Milky Way, and moves with the galaxy through the wider universe. The sun is not a solid object. It is a huge sphere of hot plasma where charged particles move in powerful magnetic fields and energy slowly works its way outward from the core. Deep inside the sun, hydrogen nuclei fuse into helium. This process releases the energy that becomes sunlight, warmth, and almost all the life-supporting energy on Earth. A photon created in the sun's core may take thousands of years to escape the dense interior. But once it reaches the surface, it travels to Earth in just over 8 minutes. The sun is a star, but it is not an unusual star in a dramatic way. It is fairly ordinary, which is part of what makes it so useful for life. It is stable, long-lived, and calm compared with many more violent stars. The sun contains more than 99% of all the mass in the solar system. All the planets, moons, asteroids, comets, dust, and spacecraft together make up only a tiny fraction of the solar system's mass. Mercury is the closest planet to the sun, but it is not the hottest planet. Venus is hotter because its thick atmosphere traps heat in an extreme greenhouse effect. Venus rotates very slowly. A day on Venus is longer than a year on Venus, which means it takes longer for Venus to turn once than it does to orbit the sun. Mars has the largest volcano known in the solar system. Olympus Mons rises far higher than Mount Everest, and its base is so wide that if you stood on its slopes, the mountain would stretch beyond the horizon. Mars also has a canyon system called Valles Marineris. It is so enormous that it would stretch across a large part of the United States if placed on Earth. Jupiter is the largest planet in the solar system. It is so large that more than 1,000 Earths could fit inside its volume, though Jupiter is made mostly of gas and liquid layers rather than solid ground. Jupiter's Great Red Spot is a storm larger than Earth. It has been observed for centuries, though it has slowly changed size and shape over time. Jupiter has a powerful magnetic field. It creates huge radiation belts around the planet, making the environment near Jupiter dangerous for spacecraft and extremely hostile for life as we know it. Saturn's rings are made mostly of ice particles, along with dust and rocky material. Some pieces are tiny grains, while others are much larger chunks, all orbiting Saturn in thin, bright bands. Saturn would float in water if there were an ocean large enough to hold it, because its average density is lower than water. Of course, no such ocean exists, but the fact gives a sense of how light and gas-rich Saturn is. Uranus rotates almost on its side. Its axis is tilted so extremely that its seasons are unlike anything on Earth, with each pole spending many years in sunlight and many years in darkness. Neptune has some of the fastest winds in the solar system. Even though it is far from the Sun and receives little sunlight, its atmosphere is dynamic and powerful. Pluto is no longer classified as a major planet, but it remains a fascinating world. It has mountains made of water ice, plains of nitrogen ice, and a heart-shaped region visible in spacecraft images. The solar system does not end at Neptune. Beyond Neptune are icy worlds, dwarf planets, comets, and distant objects that belong to regions such as the Kuiper Belt. Comets are often described as dirty snowballs or icy dust balls. When they approach the Sun, their ices turn into gas, creating glowing comas and long tails that point away from the Sun. A comet's tail does not trail behind it like smoke from a moving object. Because of solar radiation and the solar wind, comet tails usually point away from the Sun. The Oort cloud is a distant hypothetical shell of icy bodies surrounding the solar system. It may be the source of many long-period comets, though it is so far away that we have not directly observed it as a whole. The nearest star system to the Sun is Alpha Centauri. It is a little more than 4 light-years away, meaning its light takes over 4 years to reach us. A light-year is not a measure of time. It is a measure of distance equal to how far light travels in 1 year. Light travels about 300,000 kilometers per second in vacuum. That speed is so fast that it can circle Earth more than 7 times in 1 second, yet the universe is so vast that light still takes years, millions of years, or even billions of years to cross cosmic distances. The Milky Way is the galaxy that contains our solar system. It is a vast spiral galaxy with hundreds of billions of stars, along with gas, dust, dark matter, planets, and black holes. The Milky Way is not visible as a bright spiral from Earth because we live inside it. From our position, we see it as a pale band of light stretching across dark skies. The pale glow of the Milky Way is made from countless distant stars. To the naked eye, they blur together into a misty river of light. The center of the Milky Way contains a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million suns, yet it occupies a relatively small region at the heart of our galaxy. Most galaxies are thought to contain supermassive black holes in their centers. These black holes can influence the motion of stars and gas around them. A black hole is not a cosmic vacuum cleaner. Objects can orbit a black hole just as planets orbit stars, as long as they do not cross too close. The boundary around a black hole beyond which light cannot escape is called the event horizon. Once something crosses that boundary, it cannot send signals back to the outside universe. Black holes can form when very massive stars collapse at the end of their lives. If the remaining core is massive enough, gravity overwhelms all known forces and forms a black hole. Not all stars become black holes. Smaller stars like the Sun will eventually become white dwarfs, not black holes. The Sun will one day become a red giant. In the distant future, it will expand, shed its outer layers, and leave behind a dense white dwarf. A white dwarf is the leftover core of a dead star. It no longer produces energy through fusion, but it can remain hot and slowly cool over billions of years. Neutron stars are even denser than white dwarfs. They form from the collapsed cores of massive stars after supernova explosions. A spoonful of neutron star material would have an enormous mass far beyond anything familiar on Earth. Neutron stars are among the densest known objects in the universe. Some neutron stars spin rapidly and send beams of radiation into space. If those beams sweep across Earth, we observe them as pulsars, flashing with incredible regularity. Supernovae are powerful explosions that occur when certain stars die. They can briefly shine as brightly as entire galaxies. Many heavy elements were created in stars, supernovae, and neutron star collisions. The iron in blood, the calcium in bones, and the gold in jewelry all have cosmic origins. You are made of atoms that were once inside stars or stellar explosions. In a very real sense, the matter in your body has been part of the universe for billions of years. Stars are born inside clouds of gas and dust called nebulae. Gravity slowly pulls material together until dense regions collapse and new stars begin to shine. The Orion Nebula is one of the most famous star-forming regions visible from Earth. It is a place where new stars are being born inside glowing gas. Some nebulae glow because nearby stars energize their gas. Others are dark clouds that block starlight behind them, appearing like shadows in space. The colors in space images are sometimes enhanced or mapped from wavelengths invisible to human eyes. This does not make them fake. It helps us see structures and gases that our eyes alone could not detect. The universe is mostly empty space, but empty does not mean meaningless. Even the space between stars contains gas, dust, radiation, magnetic fields, and particles. There are rogue planets drifting through the galaxy without orbiting any star. Some may have been thrown out of their original solar systems by gravitational interactions. Some planets may orbit two stars at once. These circumbinary planets would have two suns in their skies, though their orbits must be stable to survive for long periods. Red dwarf stars are the most common type of star in the Milky Way. They are smaller and cooler than the Sun, and many can live for trillions of years. Because red dwarfs live so long, planets around them may have enormous amounts of time for chemistry and geological processes to unfold. But red dwarfs can also produce powerful flares, especially when young. These flares may affect the atmospheres of nearby planets. Exoplanets are planets orbiting stars beyond the Sun. Thousands have been confirmed, and the galaxy likely contains billions or even trillions of planets. The first confirmed exoplanets were not found around a Sun-like star, but around a pulsar. This surprised astronomers and showed that planets can exist in unexpected places. Many exoplanets are discovered by the transit method. When a planet crosses in front of its star from our point of view, the star's light dims slightly. Other exoplanets are found through the radial velocity method. A planet's gravity tugs on its star, causing the star to wobble slightly as the planet orbits. Some exoplanets are called hot Jupiters. They are giant gas planets that orbit extremely close to their stars, completing a year in only a few days. Hot Jupiters surprised astronomers because our solar system has giant planets far from the Sun. Their discovery showed that planetary systems can be very different from ours. Some exoplanets may be ocean worlds. They could contain large amounts of water, perhaps covering their entire surfaces or hidden beneath thick ice. Some moons in our own solar system may have oceans beneath their icy crusts. Europa and Enceladus are two of the most interesting places in the search for life beyond Earth. Europa orbits Jupiter and has a smooth icy surface marked by cracks and ridges. Beneath that ice, scientists think there may be a salty global ocean. Enceladus, a moon of Saturn, sprays plumes of water vapor and icy particles into space from cracks near its south pole. These plumes suggest a subsurface ocean and active chemistry. Titan, Saturn's largest moon, has lakes and rivers on its surface, but they are made of liquid methane and ethane rather than water. Titan has a thick atmosphere, mostly nitrogen, making it one of the most Earth-like worlds in terms of atmospheric richness, even though it is extremely cold. Earth is the only world we currently know that has life. But the search for life beyond Earth continues through Mars missions, ocean moon studies, exoplanet atmospheres, and radio searches. Life on Earth exists in extreme environments. Microbes live in deep oceans, hot springs, acidic lakes, frozen regions, and rocks far underground. Because life is so adaptable on Earth, scientists wonder whether simple life might exist in places once thought too harsh. The habitable zone is the region around a star where liquid water could exist on a planet's surface under the right atmospheric conditions. Being in the habitable zone does not guarantee habitability. A planet also needs the right atmosphere, pressure, chemistry, and long-term stability. Venus and Mars remind us that location alone is not enough. Venus is too hot, Mars is cold and thin-atmosphered today, while Earth has remained habitable for billions of years. Earth's atmosphere protects life by absorbing harmful radiation, moderating temperature, and allowing liquid water to remain on the surface. Earth's magnetic field helps deflect charged particles from the solar wind. It also creates auroras when particles interact with the upper atmosphere near the poles. Auroras happen when charged particles from the Sun interact with gases in a planet's atmosphere. Earth is not the only planet with auroras. Jupiter and Saturn have them too. The Moon stabilizes Earth's axial tilt. This may help keep Earth's climate more stable over long periods. The Moon is slowly moving away from Earth at a rate of a few centimeters per year. In the distant past, it was much closer and appeared larger in the sky. Tides on Earth are caused mostly by the Moon's gravity, with the Sun also contributing. Tides affect coastlines, oceans, and even the long-term motion of the Earth-Moon system. A day on Earth has not always been 24 hours. In the distant past, Earth rotated faster, making days shorter. The universe has no known center. In modern cosmology, space itself expands and distant galaxies move away from one another on large scales. The Big Bang did not happen at one point in space. It was the early, hot, dense state of the universe everywhere in the region that became our observable cosmos. The observable universe is about 94 billion light-years across. This is larger than 13.8 billion light-years because space itself has expanded while light has been traveling. The observable universe is not necessarily the whole universe. It is only the region from which light has had time to reach us since the early universe. Beyond the observable universe, there may be much more space, more galaxies, and perhaps a universe far larger than we can ever see. The cosmic microwave background is ancient light from when the universe became transparent about 380,000 years after the Big Bang. Before that time, the universe was filled with hot plasma, and light could not travel freely for long distances. The cosmic microwave background is almost the same temperature in every direction, but tiny variations in it became the seeds of galaxies and cosmic structure. Those tiny early variations were gradually amplified by gravity. Over billions of years, matter gathered into stars, galaxies, clusters, and the cosmic web. The cosmic web is the largest known structure of the universe. Galaxies are arranged along vast filaments, sheets, and clusters, separated by enormous voids. Cosmic voids are huge regions of space with far fewer galaxies than average. They are not completely empty, but compared with galaxy-rich filaments, they are extremely sparse. Galaxy clusters can contain hundreds or thousands of galaxies bound together by gravity. They also contain hot gas and large amounts of dark matter. Dark matter does not shine, absorb, or reflect light in the usual way. We infer its existence from gravity, especially its effects on galaxies, clusters, and cosmic structure. Dark matter appears to make up much more of the universe's matter than ordinary atoms do. The stars, planets, gas, and dust we can see are only a small part of the cosmic matter budget. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. Its true nature remains one of the deepest mysteries in cosmology. Most of the universe is not made of ordinary matter. Ordinary atoms make up only a small fraction, while dark matter and dark energy dominate the cosmic energy budget. Galaxies can collide and merge. When they do, individual stars usually do not crash into each other because the distances between stars are so enormous. The Milky Way and Andromeda are moving toward each other and are expected to merge in several billion years. The result may be a larger, more elliptical galaxy. Andromeda is the nearest large spiral galaxy to the Milky Way. Its light takes about 2.5 million years to reach us. When you look at Andromeda, you are seeing it as it was before modern humans existed. Astronomy is always a kind of time travel because light takes time to move through space. The farther away we look, the farther back in time we see. Very distant galaxies appear as they were billions of years ago. Some of the most distant galaxies observed are seen from when the universe was only a few 100 million years old. The first stars in the universe were probably very different from most stars today. They formed from mostly hydrogen and helium before heavier elements were common. The first generations of stars helped transform the universe by creating heavier elements and spreading them into space through stellar winds and explosions. Every new generation of stars formed from material enriched by earlier stars. This is how the universe gradually became chemically richer over time. Planetary systems like ours depend on heavy elements, rocky planets, iron cores, silicate minerals, and water-bearing worlds all require material made or distributed by earlier stars. The solar system formed about 4.6 billion years ago from a cloud of gas and dust. Most of the material gathered into the sun, while the leftover disk formed planets, moons, asteroids, and comets. Earth formed from countless collisions and mergers of smaller rocky bodies. The early solar system was not calm. It was a place of impacts, heat, and gradual assembly. The Moon likely formed after a giant impact between the young Earth and a Mars-sized body. Debris from the collision eventually gathered into the Moon. Earth's oceans may have formed from water already present in early Earth materials, along with possible contributions from asteroids and comets. Asteroids are rocky remnants from the early solar system. Studying them helps scientists understand the material from which planets formed. Meteorites are pieces of space rock that survive the journey through Earth's atmosphere and land on the surface. Some are older than Earth itself. Shooting stars are not stars at all. They are meteors, small bits of rock or dust burning up in the atmosphere. The International Space Station orbits Earth about every 90 minutes. Astronauts aboard it can see many sunrises and sunsets in a single day. Space is not completely silent if a medium is present, but in the vacuum between planets and stars, ordinary sound cannot travel because there are too few particles to carry vibrations. Light, however, travels through vacuum, which is why we can see stars across interstellar space. Gravity travels at the speed of light. If the sun somehow vanished instantly, Earth would not feel the gravitational change for a little over 8 minutes, just as sunlight would also take that long to stop arriving. Einstein's theory of general relativity describes gravity not simply as a force, but as the curvature of space-time caused by mass and energy. Massive objects bend light. This effect is called gravitational lensing, and it allows astronomers to study distant galaxies, dark matter, and objects that would otherwise be too faint to see. Gravitational waves are ripples in space-time caused by accelerating massive objects, such as merging black holes or neutron stars. The first direct detection of gravitational waves was announced in 2016. It came from 2 black holes merging more than 1 billion light-years away. When neutron stars collide, they can create gravitational waves, light, and heavy elements such as gold and platinum. Black holes can evaporate extremely slowly through a theoretical process called Hawking radiation. For large black holes, this process is incredibly slow, far longer than the current age of the universe. The largest black holes known are supermassive black holes with masses of millions or billions of suns. Some power bright active galactic nuclei when gas falls toward them. Quasars are extremely bright centers of distant galaxies, powered by supermassive black holes consuming matter. Some are so luminous they can be seen across billions of light years. Although black holes are dark, the material around them can glow intensely. Gas falling inward can heat up and emit powerful radiation before crossing the event horizon. The universe is expanding, and on very large scales, distant galaxies are moving away from us because space between galaxies is stretching. This does not mean galaxies themselves are expanding. Gravity holds galaxies, stars, planets, and people together while the large-scale universe expands. The expansion of the universe was discovered by observing that distant galaxies tend to have red-shifted light, meaning their light is stretched toward longer wavelengths. Redshift can tell astronomers how much the universe has expanded since the light began its journey. The fate of the universe is still uncertain in detail, but current evidence suggests expansion will continue, with distant galaxies gradually becoming harder to see over immense time. If dark energy remains similar to what it is today, the universe may slowly approach a cold, dark future known as heat death or the Big Freeze. In that far future, stars will eventually stop forming as gas is used up or locked away. The universe will grow darker over timescales almost impossible to imagine. But for now, the universe is still full of stars. New stars are forming, galaxies are evolving, and planets are orbiting distant suns. The night sky looks still, but it is full of motion. Stars orbit within galaxies. Galaxies move in clusters. Planets circle stars, moons circle planets, and space itself expands on the larger scales. Some stars move through the galaxy faster than others. A few are called hypervelocity stars and may have been flung away by interactions with black holes or other massive objects. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion like true stars. They glow faintly and cool over time. There may be many brown dwarfs drifting through the galaxy, dim and difficult to detect. Not every star is alone. Many stars are in binary or multiple star systems, orbiting one another in graceful gravitational dances. Planets can survive in some binary systems, either orbiting one star while the other is farther away, or orbiting both stars together. The universe is transparent now, but it was not always. Its ability to let light travel freely began only after atoms formed and the early plasma cleared. The atoms in your body are mostly empty space by volume, but that emptiness is structured by quantum fields, forces, and probabilities. At the smallest scales, the universe behaves according to quantum mechanics, where particles can act like waves and outcomes are described by probabilities. Quantum mechanics and general relativity are both extremely successful, but they are not yet fully united into one complete theory of quantum gravity. Understanding black hole centers and the earliest moments of the universe may require such a theory. The Planck time is an incredibly tiny fraction of a second after the beginning of the universe, before which our current physics becomes uncertain. Cosmic inflation is a theory that the universe expanded extremely rapidly in a tiny fraction of its earliest history. It helps explain why the universe appears so smooth and nearly flat on large scales. Inflation may also have stretched tiny quantum fluctuations into the seeds of large-scale cosmic structure. The Big Bang theory does not describe an explosion into empty space. It describes the expansion and cooling of space itself from an early hot, dense state. There is no known edge of the universe. The observable universe has a horizon, but that horizon is a limit of what we can see, not necessarily a physical wall. If the universe is infinite, it may have always been infinite, even when it was much denser. Infinite space can still expand because distances between points can grow. If the universe is finite, it may still have no edge, just as the surface of Earth is finite but has no edge you can fall off. We do not yet know whether the entire universe is finite or infinite. The observable universe is only our cosmic neighborhood. The largest scales of the universe are so vast that human units become difficult to use. Astronomers rely on light years, parsecs, redshift, and cosmic time to describe them. A parsec is about 3.26 light years. Astronomers often use parsecs because they are connected to the way nearby stars appear to shift position as Earth orbits the Sun. The nearest galaxies outside the Milky Way include small satellite galaxies such as the Magellanic Clouds. They are visible from the southern hemisphere. The Milky Way has smaller galaxies orbiting it, and over time it can absorb some of them through gravity. Galaxies grow not only by forming stars, but also by merging with smaller galaxies and drawing in gas from their surroundings. The shapes of galaxies vary. Some are spirals like the Milky Way, some are elliptical, and some are irregular. Spiral galaxies have arms rich in gas, dust, and star formation. These arms are not solid structures but patterns where stars and gas move through density waves. Elliptical galaxies often contain older stars and less star-forming gas, many formed through mergers over cosmic time. Irregular galaxies do not have clean spiral or elliptical shapes. They may be shaped by gravitational interactions, star formation, or past collisions. The universe on large scales looks similar in every direction. This principle is called isotropy, and it is one of the foundations of modern cosmology. No matter where we look, the cosmic microwave background is nearly uniform, with only tiny temperature differences. Those tiny temperature differences are precious because they reveal the early seeds of everything that later formed. The universe began very simple compared with today. Over time, gravity turned tiny differences into stars, galaxies, clusters, and the complex cosmic web. Complexity can grow in an expanding universe because gravity gathers matter locally while the universe expands overall. Earth is not at the center of the universe. The fact that distant galaxies appear to move away from us does not mean we are central. Observers in other galaxies would see a similar, large-scale expansion. The observable universe is centered on the observer because it is defined by how far light has had time to reach that observer. An alien civilization in a galaxy far away would have its own observable universe overlapping with ours, but not identical. The night sky is dark, partly because the universe has a finite age and is expanding. If the universe were eternal, static, and filled with infinite stars in a simple way, the sky might be bright everywhere. This puzzle is known as Olbers's paradox, and the expanding universe helps explain why the night sky is dark. Cosmic dust can block visible light, but infrared telescopes can see through some dusty regions more easily. The James Webb Space Telescope observes mainly in infrared light, allowing it to study distant galaxies, star-forming regions, and exoplanet atmospheres. The Hubble Space Telescope observes in visible, ultraviolet, and some infrared light, and it has transformed our view of galaxies, nebulae, and cosmic history. Space telescopes avoid the blurring and absorption caused by Earth's atmosphere, giving clearer views of the universe. Ground-based telescopes can be enormous, and with adaptive optics they can correct for some atmospheric distortion. Radio telescopes observe long wavelength light from space. They can study cold gas, pulsars, galaxies, and the cosmic microwave background. Different wavelengths reveal different parts of the universe. Visible light shows stars. Infrared shows cool objects and dust. Hidden regions, radio shows gas and energetic processes. X-rays show hot gas and black hole environments, and gamma rays show the most energetic events. The universe is not only seen with light, we also study it with particles, gravitational waves, cosmic rays, and neutrinos. Neutrinos are ghostly particles that rarely interact with matter. Trillions pass through your body every second without you noticing. Neutrinos are produced in the sun, supernovae, nuclear reactions, and other cosmic processes. Because they interact so weakly, they can carry information from places light cannot escape easily. The Sun produces enormous numbers of neutrinos in its core. Detecting them on Earth confirms that nuclear fusion is happening inside the Sun. Cosmic rays are high-energy particles from space. Some come from the Sun, while others come from outside the solar system, perhaps from supernova remnants, active galaxies, or other energetic sources. Earth's atmosphere protects us from many cosmic rays by absorbing and scattering them high above the surface. The atmosphere also makes the sky blue by scattering shorter wavelengths of sunlight more strongly than longer wavelengths. Sunsets look red and orange because sunlight passes through more atmosphere, scattering away more blue light before it reaches your eyes. Every clear night sky is a view through Earth's atmosphere into deep space. The stars may appear close together, but they are separated by enormous distances. Constellations are patterns we see from Earth, but their stars are usually not physically close to one another. They only appear grouped because of our viewpoint. If you viewed the stars from another part of the galaxy, the constellations would look different. The North Star, Polaris, appears almost fixed in Earth's northern sky because it lies close to the direction of Earth's rotational axis. Polaris has not always been the pole star and will not always be. Earth's axis slowly wobbles over thousands of years in a motion called precession. Seasons on Earth are caused by the tilt of Earth's axis, not by distance from the Sun. When a hemisphere is tilted toward the Sun, it receives more direct sunlight and longer days. Earth is actually closest to the Sun during northern winter, but the axial tilt dominates the seasons. The planets orbit the Sun in roughly the same plane because they formed from a rotating disk of gas and dust. The solar system is mostly flat, but comets and some distant objects can have highly tilted orbits. Asteroid impacts have shaped planets and moons throughout solar system history. Craters preserve records of ancient collisions. Earth has fewer visible craters than the Moon because Earth has weather, oceans, plate tectonics, and erosion that erase many impact scars over time. The Moon preserves ancient craters because it lacks wind, rain, oceans, and active plate tectonics. Plate tectonics helps recycle Earth's crust and plays an important role in geology, climate regulation, and the long-term carbon cycle. Earth's long-term habitability may depend partly on the carbon cycle, which helps regulate atmospheric carbon dioxide over geological timescales. No planet stays the same forever. Worlds evolve through impacts, volcanism, atmospheric loss, climate change, internal cooling, and interactions with their stars. Stars also change over time. A star's life depends mostly on its mass. Massive stars burn fast and die young, while smaller stars burn slowly and live much longer. The most massive stars may live only a few million years, while red dwarfs can last for trillions of years. Because the universe is only 13.8 billion years old, no red dwarf has yet lived out its full lifetime. Some of the stars visible in the night sky may already be gone if they were massive and far enough away. Their light can continue traveling long after they change or die. When you look at the stars, you are looking into many different pasts at once. Some light left years ago, some centuries ago, some thousands of years ago. The farther the object, the older the light. This makes the universe a natural time machine. The cosmic microwave background is the oldest light we can observe directly with electromagnetic radiation, but it does not come from the exact beginning. It comes from when the universe became transparent. Before the cosmic microwave background, the universe was opaque to ordinary light, but other signals such as neutrinos or gravitational waves might one day reveal earlier times. The search for the earliest moments of the universe is one of the deepest goals of physics and cosmology. We still do not know what happened before inflation, or whether the phrase "before the Big Bang" has a clear meaning. Some theories suggest time itself began with the universe. Others suggest a bounce, a cycle, or a deeper quantum origin. None of these possibilities is confirmed, but each shows how mysterious the beginning remains. The universe may be far stranger than our everyday experience suggests, but it follows patterns that can be studied, measured, and slowly understood. Every telescope is a kind of time machine, gathering ancient light and turning it into knowledge. Every star in the sky is a reminder that the universe is both vast and structured. Every planet discovered around another star makes the galaxy feel richer and more alive with possibility. Every galaxy is a city of stars containing worlds, dust, gas, black holes, and history. Every atom in your body has traveled through cosmic time to be here, and every quiet night beneath the sky is a chance to remember that we are part of the universe, not separate from it. The universe is not only above you, it is around you. It is beneath your feet. It is in the air you breathe. It is in the atoms of your hands. It is in the warmth of sunlight, the pull of gravity, the rhythm of tides, the glow of stars, and the silence between galaxies. And as you rest, the universe continues. Earth turns gently. The moon drifts slowly around us. The planets follow their paths. The sun shines steadily. Stars are born in distant clouds. Old stars fade. Galaxies move through the dark. Black holes wait in silence. Ancient light stretches across space. The cosmic web holds its vast shape. And the observable universe remains enormous, quiet, and deep. There is no need to reach the edge tonight. No need to hold every fact. No need to understand everything. Just let the scale of it become peaceful. The universe is old. The universe is wide. The universe is still unfolding. And somewhere, far beyond the reach of ordinary thought, light from distant galaxies is still traveling, carrying stories across the dark. For now, you can simply rest beneath that darkness. A small part of the cosmos, made of ancient atoms, held by gravity, warmed by a star, surrounded by mystery, and quietly connected to everything.